Hi folks, a quick video on the problem called row, column, and matrix views. This is an important problem because it establishes three different ways of thinking of linear algebra. One is the row picture, where we think of things as a system of equations and we're trying to find a intersection, so it's a geometric way of thinking of things in terms of rows. The second way is to think of things as a linear combination. How do I express the right-hand side vector 1, 6 as a linear combination of the two vectors that are the columns over here in the system of equations? And then lastly, how do I view this as in a matrix form, where I'm trying to find which vector xy is transformed by this matrix into the vector 1, 6. So in the row picture, I've entered both of these equations into the CAS part of GeoGebra. As you can see, they are two lines, and when we ask GeoGebra to solve that system of equations, what it finds is precisely the intersection point of those two lines. So $1, $2, comma, we're looking for x and y, and GeoGebra yields the solution -1, 3. In the column view, we're trying to figure out how I can write the vector 1, 6, which I've represented as the green vector, as a linear combination of the vectors 2, -3, and 1, 1, which are the red and blue vectors. And since we already know the answer is -1, 3, we know that we're going to be moving -1 times the red direction and then 3 times the blue direction, which of course I can get over here in my algebra window by just saying -1 times u. That'll give me that vector. And then, of course, to see the sum represented geometrically, I'm going to have to add the second vector to the tail, or to the head of the first vector. So I'm going to use the command vector start point, end point. And so I want to start where the vector -1 times u ends, which was at the point -2, 3, and I want to end at the point 1, 6. I've somehow lost. And so there is 3 times the blue vector. And so it's easily seen that -1 times the red vector and 3 times the blue vector yield the green vector. Hence the column view of this problem. So in the last segment, we're trying to find how to make the green vector as a transformation of another vector through the matrix that transforms things, or the function 2, 1, -3, 1. So I've set this up so that I can control the input vectors, two parameters, s and t, and then they give us the outputs. So I think we know the answer. The answer comes when s is -1 and t is 3. But let's play around a little bit. So in the picture, we can see the input vector is 1, 1. The matrix transforms that into the purple vector, which is 3, -2. So let's input 0, 1. And so this time the I vector gets transformed to, the J vector gets transformed into 1, 1, which should make some sense. That's the second column. The I vector, when s is 1 and t is 0, gets transformed into the first column of the matrix, 2, -3. And so we're going to search around until we can get this blue or purple vector to line up with the green vector. And let's see, get over here. And then 1, 2, 3 of those. And it's a little hard to see, but I believe you can see that the purple vector now aligns perfectly with the green vector, And which vector are we inputting? Negative 1, 3. So negative 1, 3 gets transformed into 1, 6 through this transformation. I hope that's helpful and it gives you a better sense of how we're thinking about the three different ways of viewing linear algebra.